Welcome to Math 119, Chapter 1.4, where we talk about rational expressions. We're going to be simplifying, adding, subtracting, multiplying, and dividing when it comes to these rational expressions. So first up, we have a warm-up. So just practicing how to factor. Now, if we don't know how to factor, definitely go back to Chapter 1.3, where we talk about different ways to factor. All right, so first up, we have these two polynomials. When we go to factor, we always want to be aware of a GCF. So if any of these three have something in common, we can factor it out. In this case, we don't have a GCF, and it is going to be a simple factoring, so the easier of the two, because your leading coefficient here is going to be a 1. So that being said, let's take a look at factors of 4. So things that multiply up to 4 are 1 and 4 and 2 and 2. Now in this case, we're trying to look for one of these two factors that can get us to a 3 or a negative 3. Well, this is going to be 1 and 4. So how can we arrange 1 and 4 to get us to a negative 3? And then when we multiply them together, get us to a negative 4. Well, because there is still a negative present, that means only one of your values is going to be negative. So that just means if we know it's 1 and 4 to get us to the 3, that means the bigger number, being 4, gets the sign of your term of 3, which means we're working with a positive 1 and a negative 4. So 1 minus 4 will give us to a negative 3. And then if we multiply those two together, we still keep your negative. So in simple factoring, we're able to just put these two factors right into parentheses. So these are the terms that we found to work. And again, we can always check by distributing back in. So check by foiling, you're just redistributing to each term, and you should get back to x squared minus 3x minus 4. So if that's all you needed to kind of get started with that first part of the warm-up, definitely pause the video and try it again on the next set. So again, factors of 8, after looking for GCF, which there is none, we're looking for factors of 8. So 1 and 8, 2 and 4. And we're looking for, of those factors, what can get us to a negative 2? Well, 2 and 4 can get us to a negative 2. And also, if we multiply them together, we still want that negative 8. So negative 8 being present, that means one of these two values is going to be negative. So the bigger number gets the sign of your B. So we're working with a positive 2 minus 4. And if we multiplied them back together, they will allow us to get to a negative 8. Now, because this is simple factoring, once we figure out your factors, we can just put them right into a pair of parentheses. And there you have it. So that is fully factored. Now, we also have another portion of your warm-up. Now, this one just says simplify the fraction. So simplifying 14 divided by 7, we hopefully can see that to be a 2, but the math behind it, if we want to see it, 14 has what in common with a 7? Well, 14 can be broken up as 2 times 7. And then on the bottom, you still have that 7. So when we go to simplify, the math behind it is that we're getting rid of those 7s because they're both present. They're both still they're the exact same, one above, one below, so we can actually cancel them out. Now you'll see I just left what was over here, so you could say if you wanted to break up 7 as 1 times 7, that's perfectly fine. You don't need to show that, but if you wanted to break it up into its factors, but what's left over is 2 over 1 or just 2. Now let's do it again with the one on the other side. So whether you simplified first or you went right for it, could be a little different. So perhaps you decided to break up 4 and 20. So 20 Again, having a 4 in common. So 4 times 5 gets you to 20. And then simplifying, right? You cancel it out. And in its place, keep in mind, this is why last time I showed the 1 times 7, right? 1 times 4 is 4. So you're left with 1 over 5. Much different if you just got rid of that 4 and said, hey, there's nothing there. And you ignored the double fractional sign, your division sign, right? So your answer would be a little different if you did it that way. But now you have a fraction over a fraction. Do we know what to do here? Well, it comes with an acronym of KCF. It stands for keep. Keep your sign the exact same. So if it's already positive, it stays positive. If it's negative, it stays negative. So you're going to keep the sign. You're going to change the operation. So keep what it is on top. So keep the sign. You're going to change the operation. So if we're working with division, we're now going to be changing it to multiplication. And then we're going to flip. We're going to flip the bottom fraction upside down. So twisting it upside down to be 5 over 1. Just 5. Now we could also do this a different way. So let's say you did the keep, change, flip to begin with. So you did 1 times, so keep it the same, change the operation, and then flip it, 20 over 4. And let's say this was maybe another fraction, right? It would still just remain 1 over 1 or whatever the fraction is. And to multiply these two together, fraction by fraction, we're 20 over 4. So 20 divided by 4 is again 5. So a couple different ways we can look at this one. Now the key to this one is that we are flipping the bottom fraction upside down. That will come in handy today as we're going through these rational expressions. So now let's use the warm-up and see what would happen if we had something like this being a rational expression. Well, we actually already solved these polynomials in its factored form. So from here on out, when you see any polynomial, and I'm going to put this in green. For the rest of class, I mean like the whole course, see a polynomial, we're going to factor. If you are not factoring in this class, there is something majorly wrong. And I'm actually going to shift that up right here. Okay. If you are not factoring in 119 or in your pre-calc classes, there is something wrong. We need to be factoring just about at every single term. Now, the reason why we want to factor is that we want to see, do they have something in common? So because we already factored, we already did the first part, the first step, x plus 1 and x minus 4. And then on the bottom, we said this is x plus 2 and x minus 4. Now, what do you recognize? What do you see? Well, what we have done is once we've factored, we've found something that they had in common. We had what they had, the same term in common. In this case, it's a binomial, which just like we did with something that they have in common as a 7, right? We canceled it out. It looks a little different when it's a polynomial because the whole parentheses has to look the exact same. So I'm going to encourage you to keep your parentheses here for as long as possible. Now, anytime you go and cancel something out when simplifying, you are creating a hole in your graph. So there's a hole in your graph. Well, where is the hole in your graph? Well, the hole in the graph, right, we can come from by saying, okay, well, x minus 4 is equal to 0. So x is equal to 4. This is the x counterpart of of your whole. So then we would just need to figure out, okay, well, if we wanted to know the coordinate of this, we would just plug 4 back into the equation and figure out, okay, well, or numerator should say, and figure out what your y counterpart is, right? But for now, just tell me that there is a whole when x is equal to 4. So then the remainder of the problem, we have x plus 1 over x plus 2. Now, a lot of students, if they don't use these parentheses, they are very, very tempted to then go ahead and cancel these x's out and just say the answer is 1/2. That's incorrect, because when you see addition or subtraction signs, you need to be super careful when simplifying. Do not be tempted into canceling too much. When we go ahead and cancel with polynomials, they have to look the exact same with your parentheses. So that's why I'm going to encourage you to keep parentheses around it so you're less tempted to be too canceling. Now, let's take a look at your graph before we go any further. So what do you notice is happening with your graph? Now, this graph is represented with this rational expression. Well, what do you notice, right? Think about some things that we might have. Well, we do have the whole here, which we said was that x is equal to 4. So 1, 2, 3, 4, that is your x value. That is where that whole is appearing. Now, what other special features do you see from your graph? Well, we do have a y-intercept, so that's pretty clear over here. Again, to find your y-intercept, as you would normally with your y-intercept, we can set x equal to 0 and figure it out pretty quickly. Whether that is in your factored form or your original, right? Setting all of these values equal to 0, you have -4 over -8 for a positive 1/2. So you'll see that right here. So 0 and 1/2. What else do you notice? Well, we also, kind of going that same idea, we also have an x-intercept. Where is this x-intercept? Well, it looks to be when x is equal to -1. Where is that information coming from? Well, taking a look at your simplified form might give us that suggestion. Well, your numerator is x plus 1, so there's probably some connection there. So if we're looking at your x-intercept, right, your x-intercept provides your numerator provides your x-intercept. So x plus 1, we can set that equal to 0, just as we've done with, well, I guess we haven't done solving quite yet, but this is going to be our precursor to what we're going to be doing in chapter 1.8, where we're talking about solving, right, finding x-intercepts. But this is where your x-intercept is. This is when your y value is equal to 0 and your x value is equal to some number, so -1, 0. Now, we will be graphing these rational functions in chapter 5.5, right? So this is kind of just extra knowledge so that I'm exposing you a little bit early so you're not super surprised by the end of it. So we have numerators in your x-intercept. Or sorry, your numerator provides your x-intercept. Now, what else is given? If your numerator is giving your x-intercept, what the heck is your denominator giving you? Well, your denominator is giving us something called an asymptote. This is where, well, what is an asymptote, right? This is where we have a line that your graph cannot cross. So your graph, you can probably tell there was something weird happening with your graph. And don't worry about this little cusp here. That was just human error. I couldn't get these to match. But where is this vertical line? Well, this is a vertical asymptote. So this vertical line is that x is equal to -2. So where's that -2 coming from? Well, we just said this is where your denominator comes into play. So your denominator your vertical asymptote is from your denominator. So when x plus 2 gets set equal to 0, you'll notice that x is equal to -2. Now, why is it that way? Well, because it's in your denominator, right? What value is never allowed in your denominator? Well, that would be 0. So in this particular variation, if we let x be -2 and we add it to 2, well, this will be where an x value of 0, or sorry, a value of 0 occurs, which would cause it to be undefined. So different variations will provide us with different asymptotes. Now there's one more thing that I'll just show you on the graph, which we won't cover until later with the graphing portion. But you also have a horizontal asymptote. This is at y is equal to 1 in this case. And that is coming from a special case. So this is when you have the matching degrees. If they're the exact same, you look at your coefficients, your leading coefficients. But we get more into that later on at 5.5. But I will be asking you throughout this video what your vertical asymptotes are, maybe what your numerator is, do you have any holes, and things like that. Okay, so we did just say what happened to x minus 4, right? Well, at x minus 4, we said creates a hole. Now, why is this important? So other than it creates a hole, it actually kind of messes up your domain, because next up, I am going to ask you what's your domain, right? So based on this graph, can you come up with an appropriate domain? Keep in mind, with this vertical asymptote right here at x is equal to -2, we are not able to cross. That's why your graph does weird things. We're going to try to get as close as we can to where x is equal to -2, but we're not going to cross it. So how does that mess up your domain? What does your domain look like? Well, if you have an asymptote at -2 and a hole at 4, coming back to our idea back in 1.1 where we talked about interval and graph notation, you have x is equal to -2, which provides us with an asymptote, and we have x is equal to 4, which is the hole, and an asymptote. These are values that we'll have to skip over, right? So we're not able to be these values. So we're going to be jumping over these values and continuing on. So from -infinity to infinity, there's only 2 numbers that we are not allowed to be. So what does that look like in terms of your domain? Well, your leftmost value is your smallest value, your -infinity. And we go all the way from -infinity, and then we get really, really close to -2. Can we achieve -2? No. Then we use this union sign to tell us, hey, this is a continuation. It's also, or. And then we go from -2 all the way to 4. Again, are we allowed to be 4? No. So we're going to jump, create a union one more time, and then 4 to infinity. Now, I think on your homework, it'll just say, hey, what are some excluded values or restricted values? In which case, x is not equal to 2 and not equal to 4. So this is what you can provide on the homework. But otherwise, what we're going to be doing on your test more likely is I'm going to ask you for the domain of the function. Okay. So now real quick, can you go ahead and pause the video and see if you can simplify these 4? All right, I'm hoping that you are coming back. So you'll notice that your first one, we have 10 and 12. right? 10 and 12 have what in common? Well, they have a 2 in common. So we'll break these both up into 2. We can cancel out the 2, and you're left with 5/6. Now, if you already knew what that was and you can just see it, awesome. Just jump right into 5/6. Now let's try it again with your next one, right? Are we allowed to just cancel out these 10s? No, right? A lot of us will not cancel out the 10s because 10 plus 2 is a number, right? So 10 plus 2 will provide us with 12. And then we put it over 10, right? And then again, you can simplify 5/6 and great. Now, why did I put that one on there? It seemed kind of silly. Well, what do you think students do here? Maybe you did it, or maybe you didn't, right? But x over x plus 2, did you go ahead and cancel these x's out? No, you didn't cancel out these 10s because these are in fact just numbers, the future numbers, right? So try not to be tempted, right? When we go to cancel these out, we have to have parentheses to group them. They have to have the exact same thing above as they do below. So in simplified terms, this is it. Do not cancel. And of course, your last one, we finally do have a situation where they are the exact same, and we can go ahead and cancel. A 1 is in its place, and we have x plus 3. So when can we cancel out and when can we not cancel out? Pretty much just be cautious. I can't spell today, cautious. That looks so bizarre. Well, I'm just gonna write, be careful if adding or subtracting binomials. Make sure parentheses are exact same. Okay. So now go ahead and pause the video now and see if you can handle the next 3. Okay, even if you kind of just get started, think about what we did at the very beginning of this one, right? We said, oh, well, we see a polynomial, we are going to go factor. So first up, let's factor. So this first one is a special one. We have the difference of squares. So this is when we have x plus 2 and x minus 2. If you don't know how to do that, please go back and watch 1.3. And the next one, right? What do these have in common? Well, there's a GCF of an x in common for an x minus 2 left behind. Now, what is what's going to happen next? Well, they both have an x minus 2 in common. Those parentheses match. So we have x plus 2 remaining over an x. Now, what happened when you canceled out the x minus 2's? Well, you created a hole. So we have a hole at x is equal to positive 2. So just do a sign change for me on that one, or you can set it equal to 0 and then do the sign change. So we have a hole at x minus 2. Okay, and we'll come back and talk about domain here at the very end, right? And maybe even 1 or 2 of these we'll talk about your x-intercept, because our main goal right now is just to simplify. All right, so let's try it again. So simplifying, factors of 6 that add or subtract up to a -1. We have x minus 3 and x plus 1. So sorry, x plus 2. Again, just how we do it is 1 and 6, 2 and 3, right? Looking at these factors, 2 and 3 can get us to a -1 if and only if we are subtracting 3 and adding 2. And if we go ahead and multiply, we will get back to a 6, a -6, that is. Now notice that we have 3 minus x. even if we rewrote it and had x plus 3, right? That's not exactly what we need. We're looking at noticing, hopefully, that these are kind of close, but just need an alternate sign change. In addition, a lot of your instructors in the future, they might not like you to have this negative leading coefficient, so they might even have you factor out the negative anyways. So factoring out the negative, we have negative on the outside, and changing all of your signs will then provide you with the same exact parentheses on top as you do on the bottom. So in which case we're able to cancel. And when we go to simplify, we're leaving behind an x plus 2 over a negative 1. Now, a lot of us at this point can just conclude that we have a negative x plus 2. Your homework is going to get a little picky with Hawks Learning. It will not let you do negatives in the denominator a lot of the times. So just pop it up to the numerator, put it out front, as long as there's a pair of parentheses out there. All right, before we move on, you did some canceling. So what did you make? Well, we made a whole. I'll do it over here. We made a whole. Where is the whole? When x is equal to a positive 3. All right, last up, we have this one. Okay. So we have 2x squared plus 7x plus 3. Now, this one is your complex, complex factoring, because your leading coefficient is not a 1, so it's a 2. And none of your terms have anything in common, so we can't factor out a GCF. So let's take a look at how we tackle this one again. A further in-depth process of it, we can look at in chapter 1.3. 1.3. So we're going to be looking at AC grouping. So 2 times 3 get us to a positive 6, 1 and 6, 2 and 3. And we're trying to figure out how we can rearrange this to be a positive 7. So 1 plus 6 can get us to a positive 7. And if we multiply them together, they do allow us to get us to a positive 6. So we get to rewrite 7x as 1 and 6x, or 1x and 6x. You'll see that change right here. And then we get to factor with grouping. So grouping the first 2 and the last 2 along with the sign, factoring out a GCF from both. Don't forget, you still need your placeholder value. Taking out a 3, so we get 2x plus 1. And as long as your parentheses match, you did it correctly. So these parentheses here, they match. So we're left with x plus 3 and a 2x plus 1. Now, if you watch the other video about slide and divide, you can certainly do slide and divide here on this one as well. Just pick one of the two, or just pick any method that you are comfortable with. Although if you are doing slide and divide, do not forget to divide. If you are a forgetful person, I do not suggest it for you. All right, taking a look at your bottom one, we're looking at factors of 15 that can get us to a negative 2. So 3 and 5, only if 5 is negative and 3 is positive. So we have x plus 3 and x minus 5. Going to simplify, we can simplify those 2 values out, or those 2. And again, we're creating a whole at x is equal to negative 3. And your final answer is 2x plus 1 over x minus 5. Okay. Now, before we just go right into domain on the bottom here, let's first just look at the domain of what we have from the above, right? If we're talking about domain or restricted values, right? The most restricting value you have is anytime a 0 is in the denominator. So looking at your ending value, right, your ending simplified form, if you still have something in the denominator, we have to set it equal to 0. So other restricting values, so I'm going to write this as a vertical asymptote, VA, at, well, where is it at? Well, this is when you get to put your denominator in. So we have your denominator when x is equal to, and we always set it equal to 0, so it happens to be that there's a vertical asymptote at x is equal to 0. So again, this is for your restrictions. We have a vertical asymptote at x is equal to 0, so we cannot be equal to 0 because it'll provide a 0 in the denominator, undefined. As well as if we put a 2 into your expression, right? If we put it in here and put in a 2, that'll negate everything. So this would become a 4 minus another 4, which gives us a 0. So again, x cannot be equal to 2. So what that looks like on a graph notation, we said 0 and 2, we're going to be skipping over. So what does your domain look like? Well, your domain, we're going to be going from negative infinity to 0, union, 0 to 2, union, 2 to infinity. So looking at your domain, we're looking at any holes you may have created, as well as anything that's left over in your denominator. Again, anything in the denominator, you'll be having a vertical asymptote. So let's try it again on your next one. So do we have a vertical asymptote? Is there anything in your domain at the very, very end? You might say, okay, well, yeah, there's really a -1 in there, but as long as there's no variable in there, we're okay. So your vertical asymptote, you can write none. So no restriction for the denominator, but restricting values, we still have the whole when x is equal to 3 that we cannot be, right? The whole is going to provide a gaping hole in your graph, which we have to skip over. So one more time, with your domain, we have the whole at 3, we'll skip over. So again, what is this going to look like? Well, we're going from negative infinity to 3, union, we're jumping over 3 and going all the way over to infinity. Okay, now if you haven't paused the video yet to try out these domains yourself, definitely do so here. Okay, vertical asymptote, where would it be? Right, so in your domain, your denominator, we still have x minus 5, so let's set that equal to 0. So x is equal to 5. This is where your vertical asymptote is, where we can't touch, right? We can get super, super close to this value, but we can't touch it. So that means we're restricted. Our restrictions are from your vertical asymptote when x is equal to 5 and the whole when x is equal to -3. So we cannot be these values. So if we were to draw a little graph notation, we have -3, we have 5, jump, jump. So once more, we're going to go from negative infinity to -3, union, -3 to 5, union, 5 to infinity. Now, the last kind of tidbit that I can kind of provide for you guys is just by looking at, for the future, strictly for the future, what is going to be your x-intercept? Well, your x-intercept is coming from your numerator. So x-intercept, this is when x is equal to 2, so 2, 0. See if you can find the remaining x-intercepts. This is when x-intercept here again is equal to -2. And on this one, the x-intercept would be when x is equal to -1/2. So -1/2 comma 0, 0. And there you go. All you have to do is set, oh, I'm so sorry. This should be negative, not positive. All you have to do is set these parentheses equal to 0 to determine where these x-intercepts go. Now let's take a look one more time at your domains, because we do it quite often, because we are going to be gearing up to graph here. So your domain, on if you're just given x, or even if you just say, okay, y is equal to x, are there any restrictions? No, there's no restrictions. X can be any number under the sun. This is because if I asked you to graph it, you can pick whatever values you want for x, right? X is 0, y is 0. X is 1, y is 1. X is -1, y is -1. So you're creating a nice solid line, in which case your domain here, there's no restrictions, there's no holes, there's no vertical asymptotes. We don't start in a funny position. So your domain here is all real numbers. Now, if we change your variation ever so slightly, we have y equals 1 over x. Well, now x is in the denominator. So what value is not ever allowed in the denominator? Well, x cannot be 0. So it can be any number besides 0 in the denominator. So if we were to do some little number line, we now have a vertical asymptote at 0. So we can be any number besides 0. So again, -infinity to 0, union 0 to infinity. We are just skipping over this one value. Now we don't know it yet, but the graph to this, what it looks like is this over here, where that x is equal to 0 is right here. This is when x is equal to 0. So you're noticing that vertical asymptote. All right, one more time, right over here. Now, are there any restrictions here? Are there any sort of values we need to be aware of? No, because we do not have a denominator, right, other than 1, right? But we don't have a denominator to give us any sort of restriction. So this is another one where the domain is going to be all real numbers. Now, if you already know what this graph kind of looks like, or even just a general shape, this is going to kind of look like a U shape, a parabola. And we'll learn how to graph these in chapter, I want to say it was like 3.3. So we'll learn how to graph parabolas in 3.3, and then some higher ordered polynomials in 5.1. But for generalization, anything with a squared term that does not have a denominator will have all reals. Now, the next variation, very similar. We now have that same value, but in the denominator. So that's going to provide us with some restrictions, which what is not allowed in the denominator? Well, 0 is never allowed, right? And just as we did before, we see a polynomial, we're going to have to factor. So factoring out your GCF, still setting it equal to 0 or not equal to 0. So you have two pairs of parentheses, two restrictions. So we can say x and x minus 2 is not equal to 0. In this case, you have two vertical asymptotes, one when x is equal to 0 and another when x is equal to 2. So therefore, we cannot be 2 and we cannot be 0. Don't forget, any sort of GCF you might pull out still matters. All right, try that domain. And how did you do on that domain? So to kind of sum up, if you do have any sort of denominator, you're going to have a restriction no matter what. Whether that causes a whole or a vertical asymptote, it still matters. Now, before we get into adding and subtracting rational exponent or rational expressions, let's actually skip and do something a little easier. Let's do multiplying and dividing rational expressions. So multiplying and dividing fractions, it tends to be a lot easier than adding and subtracting. So we're going to start here. So now, how would you simplify these two expressions? So what I'd like you to do is pause the video and see if you can attempt doing it on simpler fractions before we go ahead and get started. All right, so looking at multiplication, right? There's a couple different ways we can do it. One of which is we just multiply your numerator straight across and your denominator straight across. So that might be one game plan that you come up with. Perhaps you get 45 over 12. And then in this case, we're going to have to recognize, well, what do 45 and 12 have in common? Well, 45 and 12, they both have a 3 in common. So 3 times 15 and 3 times 4 will then allow us to cancel out your 3's, and it's left with a 15 over 4. So this process is a little bit more tedious because you have to multiply sometimes some big numbers. Now, if you did this other method, you might have done it a little quicker. So it's not called cross multiply. It's more of a cross cancel. Cross multiplying is when you have an equal sign in the middle. So looking across each side, we can see, well, do they have anything in common? So does 5 and 4, do they have anything in common? Well, no. But does 9 and 3, do they have anything in common? Well, yeah. 9 can be written as 3 times 3. And you have the 3 directly across, or 1 times 3 directly across. So in which case, one of these 3's cancels with the other. You can't cancel out double. That would be too much. So in which case, you're left with 5 times 3 and 1 times 4 to make 15 over 4. And the reason why you have to do 1 to 1 is that when you go to multiply these together, right, it's really 5 times 9 over 4, or sorry, 3 times 4. Or if you kind of think about it, you could do 9 over 3, right? All you do is you can kind of reverse it and then divide, right? But 9 divided by 3 is still 3. So you can't just cancel this whole thing out because that wouldn't be quite right. All right, let's take a look at what the division side looks like. So you have 2 divided by 7 divided by 4 divided by 5. So if it looks confusing this way, we can always go ahead and rewrite it. You have 2 over 7 being divided by 4 over 5. Now, have we seen something like this recently? Hopefully we said yes, because in our opener, we were working with a fraction over a fraction. It just didn't look exactly like this, right? Just a different variation. So when you have a fraction over a fraction, right, what did we do? Well, we said keep, change, flip. Keep your sign. So 2 over 7, it's positive. It just stays as is. You're going to change the operation. So instead of division, it's multiplication. And then you're going to flip the bottom fraction. Always flip the bottom one. Always flip the right one. 5 over 4. Then you can go ahead and try to multiply or cross cancel. So whether you said, well, this is 10 over 28 and then simplified, or if we kind of use that new strategy, right? This 4 really is made up of 2 and 2. So canceling one of your 2's out. You get 5 over 7 times 2, which is 5 over 14. So this is kind of the basics of what you would do with a fraction. Now let's see what we would do when we have something a little bigger with a rational expression. So keeping those same thoughts in mind, right? Let's try this out. See if anything can cancel as we go to simplify. Well, we do see a bunch of polynomials, right? And we cannot cancel these two values. We cannot just cancel, oh, this x with this x and that x with that. That's not how this works, right? Think about these as being parentheses. They have to look exactly alike for us to cancel them out. So when we see these polynomials, go ahead and factor. So step one, factor. So factoring the top, we're looking at factors of 10 that can get us to +3, but multiply to -10, right? So 2 and 5 will get us there as long as 5 is positive and 2 is negative. So x minus 2, x plus 5. Now your bottom is already as simplified as it can be. We're multiplying x minus 3. And then doing the same below it, we're looking at factors of 2, 1 and 2, and we're looking for a -1. So the bigger number gets the sign. So -2 plus 1. And if we were to multiply those together, we still get your -2. So x plus 1 and x minus 2. So now doing the same idea as we did over here, right? Let's go ahead and see if anything across or up and down can cancel us out, make our life a little simpler. Well, directly across, we notice that there is an x minus 2 and an x minus 2. So these can go ahead and cancel. Again, every time you cancel, you're making something, right? So then we get x plus 5 and an x minus 3 over x plus 3 and an x plus 1. So as long as nothing else can cancel, we're done. Now we always want to keep this in its most simplified factored form. Keep in factored form. And I get it every semester. I'm not sure why. I get it every semester. Students start to foil and foil and foil, and then they get lost and it's messy and it's crazy. If you're getting lost and if it is crazy, we did something wrong. Start with foiling or start with factoring, see if they cancel, and keep it in the factored form. Okay? Do not multiply. Do not multiply. All we did, we chose to factor and simplify. All right. So on our next one, if we're looking at it from this one, right, we see a bunch of polynomials. What are you going to do? So game plan, first factor. Now we already factored this top one. It's the same one as the one before. So we have x plus 5 and an x minus 2 over 3x divided by, we have to factor this one, x minus 2 and an x minus 2, and then a 9x cubed. So first up, let's factor. So first, factor. And then let's go ahead before we start to cancel, right? Because nothing in its direct setup will cancel. And if you did combine these to make x minus 2 squared, you're not wrong. I want to leave it expanded for now, and you're going to see why. So now let's take a look at this division sign. Well, what did we do from our problem just before it, right? With the division, we said, well, really, we can rewrite it as this one, right? So we're going to flip the rightmost one. We're going to flip the bottom one. So flipping this upside down, we're keeping the left side the same. We're changing the sign, so it's now multiplication. And then we have 9x cubed, x minus 2, and an x minus 2. So what happens now? Well, now we can go ahead and cancel. But again, only canceling one for one. You cannot cancel out both. Do not cancel out both. Can anything else cancel out? Well, 9 can be written as 3 times 3, and there are 3 x's here, right? There's 3 x's here, so be super careful when canceling. This x will cancel out with one of the 3 x's, because this is really x times x times x. You're only canceling out one of these x's. So your final answer should be 3 from the leftover 9, 2 x's times x plus 5 all over x minus 2. So to kind of rehash, you're going to factor first, then you get to simplify, and then leave it in its factored form. Okay, let's see. All right, so now we're going to be moving on to adding and subtracting. So combining rational expressions by adding and subtracting. So just like we did in our previous one, let's see if you can add and subtract just with regular fractions before we make anything a little more complicated. Okay, so if we're looking at your fractions here, we have 1/3 plus 3 over 4 minus 5 over 6. Now we're looking at a least common denominator, an LCD. So your least common denominator is the smallest number that can these ones fit into. Now, what could that be? Well, your least common denominator in this case is going to be 12. 12, right? Well, I should say, if we have trouble with least common denominator, right? 3, well, 3 times 1 is 3. 2 times 3 is 6, 3 times 3 is 9, and 3 times 4 is 12. So sometimes you can write out a few of these to get started for your LCD, right? Do the same. 1 and 4 is 4, 2 and 4 is 8, 3 and 4 is 12. So if you're noticing, okay, well, these actually already have a 12 in common, that looks promising. And then if you already know, well, what does 6 have in common, right? 1 and 6, 6, 2 and 6, 12. And just like that, your smallest number that these have in common is a 12. Now, they do have more in common, right? Other common denominators that they could have, if we kept going, right, would be what? Well, actually, I don't want to give it away, right? So your LCD, in this case, your least common denominator is 12. But your common denominator, a denominator that we can get them all to be the same, like what else could it be? Well, it could be 24, it could be 36, and it could continue, right? 30 or 3 times 8 could give you to 24, right? 4 times 6 can also, yeah, it can also get you to 24. 6 times 4. I don't like how I wrote that. There we go. 6 times 4, 24. 4 times 6, 24. 6 times 6, 36. Let's see. 9 times 4, 36. And what is that? 12 times 3, 36. Right? So all of these numbers, while they do fit, the reason why we want your LCD is that we're making it a little bit easier for us in the end process. So we're going to be sticking with 12. Okay. So that just means if we figured out your LCD, right, let's make all of your denominators have the common denominator of 12. Right? Because we can't just add these fractions together. They're so unbalanced. One is in thirds, the other's in fourths, and another is in sixths. So let's make all of these denominators into 12s. So 3 times 4 is 12. What you do to the bottom, you do to the top. 4 times 3, what you do to the bottom, you do to the top. 6 times 2, and over that. So then we have 4 over 12 plus 9 over 12 minus 10 over 12. So we really have 4 plus 9 minus 10 all over 12, which then is 3 over 12, or 1/4. Right? So the big picture, the big takeaway is to find your least common denominator in order to add the numerators together so that it makes the process of simplification easier. Otherwise, you're left with really, really big numbers, and sometimes we kind of get lost. So the same thing over here, right? Your least common denominator, right? We can do common denominators all day long. So figure out what your least common denominator is. Now, if you kind of get stuck, think about 1 over 3 plus 5 over 6, right? So what's your common denominator? What's your LCD here? Your LCD here is 6. We can make 3 into 6 really easily. But why is that? Right? I already know, okay, I can multiply this to make a 6. Great. But the reason we know that it's a 6 is because 6 is really 2 and 3. So if we were to rewrite this 6, we can say 2 and 3. These 3's match here, but what the 3 was missing is the 2. So we are going to multiply this side by what is missing. So you're going to multiply by only what is missing. So looking at these two x's here, what's missing? Well, if we write this one on the right-hand side, right, x squared, well, x squared is really just x times x. These two x's match, which means how many x's are missing from the other one? We're missing just this one x to make the other one x squared. So your LCD here is x squared. Whereas your common denominator, you could have done x squared, you could have done x cubed, x to the fourth, x to the fifth. You could have kept tacking it on, but it's going to get really complicated really quickly. So instead, right, what you do to the bottom, you do to the top. Then we have 3x plus 1 each over x squared, and do not go backwards. Do not cancel this out because then you're all the way back to where you started. No. So we're going to write 3x plus 1, put them in parentheses, and put it over your common or least common denominator. So do not get rid of your least common denominator. Do not cancel. We got to do it this way, right? This is the way. Now that whole thing, step by step, is down here if you need that explanation one more time. So a common denominator versus the least common denominator, it just means that we don't have to simplify so much at the very end. So let's take a look at your first variation. So first up, just as we've done in the past, you see some polynomials, we should then start to factor, right? Can we factor these ones? No, not yet. We also cannot just cancel, or cancel these ones out, right? We cannot cancel unless they look the exact same. So let's go and factor. This bottom one over here is extra special, right? This bottom one can be written as x plus 3 and x minus 3. So then what on the other side do we notice about your denominator? Well, they both have an x plus 3 present. So that just means we're going to have to multiply by what's missing. So what are we going to multiply the other side by? Well, we're going to multiply it by an x minus 3. What you do to one side, you do to the other side. So when it comes to your LCD, what should it look like? What is going to be on the denominator? Well, your denominator, we have x minus 3 and an x plus 3. So step 1, find an LCD. Step 2, let's just rewrite what we have. Again, do not go backwards. Do not slash these out because then you are back to where we started, right? So do not cancel. Instead, what can we do? Well, we're going to go ahead and FOIL. So go ahead and FOIL here. Start to simplify. Now, if you don't know how to FOIL, please go back to, I want to say that was in 1.2, maybe 1.3, definitely 1.3. So we have x squared minus 2x minus 3, excuse me. And then we have your plus 3x all over x plus 1 and an x minus 3. Okay, so from here, right, combine your like terms. So let's write that. So combining your like terms, you get x squared plus x minus 3 over x plus 3 and x minus 3. Now, before you say we're done, definitely check to see if your numerator is factorable. Sometimes it is, sometimes it isn't. In our case, ours is not factorable, so we are done. Keep your denominator in its factored form. And there you have it. So pause the video, see if you can try it on your next one. All right, so let's go ahead and start to factor. So on one side, we have x minus 2 and an x plus 2. And on the other side, we have x plus 2 and an x minus 1. All right, so do they have anything in common? Oh, yeah, they have a 2 or an x plus 2 in common. Now, what is missing from your left-hand side, right? Well, if I rewrite it, so we get 2x minus 1 over x plus 2, x minus 1 minus 2x. There. I don't know why I try to squish things sometimes. Right, from your left-hand side, well, what's missing from its denominator? Well, the other one has an x minus 2. So this one needs an x minus 2. So we'll multiply that one over here. What you do to the bottom, you do to the top. And then on the other side, right? On the right-hand side, what does it need that the other one has? Well, it needs an x minus 1. So we're going to multiply that one over. An x minus 1. What you do to the bottom, you do to the top. Now, before you start going into the FOILing, I want you to put a parentheses if there's not one already. The reason for that is with your subtraction sign, you're going to be distributing it throughout your problem. It's not so bad when you have a monomial, but the second you have a binomial, so let's say this was 2x plus 1, right? A lot of students just say, oh, well, it's really negative 2x and then the plus 1. No, you can think about this as being plus a negative, and then the whole thing is negative. So anyways, you got an x minus 2, a 2x minus 1 over a negative, nope, I just said use parentheses. And then in your denominator, right, your LCD will be showing this one, x minus 2, x plus 2, and an x minus 1. Again, do not cancel. So if that's all you needed, try and see if you can finish out the remainder of the problem on your own. We're going to FOIL to get 2x squared. Let's see. So sorry, 2x squared minus, where am I? So sorry, plus x minus 4x plus 1, no, plus 2. So that's on one side, minus 2x squared plus 2x on the other. Minus 2, x plus 2, and an x minus 1. Let me just see that I checked and did that right. A little on the distracted side. Nope, that's a minus. There we go. There we go. Okay. Combining your like terms. All right, so things that can combine, let's see. We have 2x, or 2x squared and a negative 2x squared, so those are going to cancel. We have a negative x minus 4x plus 2x, so those are going to combine, and then we just have a positive 2. So up top, oops, wrong color. So let's see, a negative 5x plus 2x is really just a 3x plus 2, a negative 3x plus 2, that is. X minus 2x. And checking to see if the top is factorable. We'll know it is not factorable, but you do have a negative leading coefficient. So one more time, I'm going to write this out, which for me, it's easy. Just gonna copy, paste, and go. And just change up your numerator. This is the better answer. This one is okay. I'll give it to you on the test. The other one is what I really want to see. Again, I won't take off points, but future instructors, they might. All right, let's try it one more time. Now you'll notice that these two, they actually do not have anything in common, which I think sometimes is the easiest variation of all, because you actually just get to multiply both of them together because they have nothing in common. They don't share anything. So that means we get y plus 4 times y plus 2, because really this one needs a y plus 4 and a y plus 4. And the other side needs a y minus 2. So plus 6 minus, or y minus 6, y minus 2, y plus 4, and y minus 2. All right, then we are FOILing it out. So FOIL. And then let's combine your like terms. So we have y and y squared. Let's see what else we have. We have these two, and we have these two. So you have 2y squared minus 2y plus what, 20 over y plus 4, y minus 2. Check to see if it is factorable. Let's see, hold on. Combine. Factorable. All right, is it factorable? Yes, a little bit. We have a GCF here. So taking out a 2, we get y squared minus y plus 10, which that is not factorable. So we'll have to leave it there. you go. So that is adding and subtracting rational expressions. Again, just one tidbit, make sure if you have a subtraction sign to put parentheses around your term, whether it's a monomial or binomial, just be super careful. Now, I do want you to note this line is something that you might be seeing in the future. So I would put some stars around it to alert you to your notes. Hey, come back to this one before any sort of assessment because I do like it. Okay. So now let's look at example 4. So now we're going to be simplifying complex rational expressions. So these are complex fractions that look like a mess, but we're going to make it look better. So first, let's take a look and see what skills we picked up from this video. So in example 1, so looking at example 1, what did we learn how to do? Well, we learned how to simplify. So we factored and simplified, right? We've got to cancel stuff out. Example 2, so this one, right? What did we learn how to do? Well, we learned how to add these two crazy looking fractions, right? By getting a common denominator. And in example 3, what did we learn? Well, we learned then how to multiply and divide. So probably a keep, change, flip going on, right? So from all of your examples, we learned something new. So how to simplify. How to find LCD for adding and subtracting. And the last one, how to multiply and divide. So like a keep, change, flip situation. So we're going to be simplifying, we're going to find a common denominator and do a keep, change, flip. So each of these skills we need for when accomplishing one like this. So while it looks like a complete mess, break it up into 2 mini problems, something that we were talking about from 1.2, where we said if it looks complicated, just break it up into parts. So first, let's tackle your numerator, right? Your numerator is a bit of a mess. So you'll notice that we have 2 sides, there are 2 fractions. They don't have the same denominator, so we have to find a common denominator. So what is it? Now, if you're saying h, which I understand, you can't just say, oh yeah, plus h, and that's great, they match. No, right? Think about what we've been talking about. These are really in parentheses. They have to match. This x is not the same as this x. So multiply by what is missing. So one side needs an x plus h. What you do to one, you do to the other, or bottom to top. And on the other side, it needs just the x. So really you have x times 1, just x, minus the x plus h, all over your least common denominator of x plus h. Again, do not go backwards. Do not just cancel and just say, oh, yep, it's a -1. Nope. You worked so hard to get to this place. Do not move backwards. So find an LCD is your first one. So find LCD. Then simplify your numerator. So let's see, we got x minus h. So distributing that negative throughout the entire parentheses. And then you'll notice that in your numerator, these 2 terms are going to cancel and you're left with negative h. Okay. So now once it looks simplified, right, just kind of keep it as is. Keep it normal. So then we look to your denominator. So we do the same thing with your denominator if it looks a little complicated. Now, in our case, your denominator is just h, so we can bring these 2 ideas together. So let's bring your numerator and denominator into one. So numerator, we said, is negative h over x plus h, all divided by your denominator of h. So now what are you going to do? Well, you have a fraction over a fraction, right? You can keep this h over 1 if you need to see that keep, change, flip. Keep, change, flip. Keep everything the same in your numerator. Change the operation, so go from division to multiplication, and then just flip your fraction. So 1 over h. At the very end, now you get to simplify. So what can simplify? Well, these h's can simplify, and you're left with negative 1 over x plus h. So that looks a lot better. Hopefully that wasn't too bad. I would like you to pause the video and try it again on your own with B. All right, so take a look at your numerator. Not super crazy. We do have a polynomial, so what are you going to do? Well, with your polynomial, we are going to factor it out. Don't forget your placeholder of 1. So GCF factoring, take out a 6. Let's look at your denominator. So not as easy, not as great, or as simplified. Now, if you have a whole number, always put it over 1 if we're talking about figuring out a fraction. So what's your LCD here? Well, your least common denominator is going to be x squared. It is very, very easy to make this one into an x squared if you just multiply by an x squared. So we get 3x squared minus 3 over an x squared. Now let's take a look. Can we keep going in your denominator? Yeah, what do you notice that these the numerator has in common? So simplify. Take out a 3, x squared minus 1 over an x squared. Can you keep going up here? Absolutely, keep simplifying, see if you can factor. You want to do it now versus later, because sometimes later you think you're done and you're not actually done, you're not quite there. This is really x plus 1 and an x minus 1. It just tends to be that students kind of forget if they don't do it right here, right now. So kind of always ask yourself, am I done? Is it factorable? Things like that. Okay. So while it does look a little bigger is okay as long as it's more in its factored form. So now let's bring these two ideas together, your numerator with your denominator. Let's see, I will put that maybe over here. So you get 6x minus 1 over 3x plus 1, x minus 1 over x squared. So just as you did before, keep, change, flip. You can say that this is still over 1 times 3 times x squared over 3x plus 1 and an x minus 1, and then go ahead and simplify. We're leaving behind a 2 here. The x minus 1s can go. So we're left with 2x squared over x plus 1. And there you have it. So that is how we can get to simplifying complex fractions.